All right, I'm going to try to make some catch up here from I'm behind in some notes, but catch up. Here's week 6. We're talking about forced vibration with damping, and that is section 3.1 in the textbook, and these are associated with problems 3.1 through 3.5. All right, so we can do lots of different types of patterns of repeated forced vibrations onto a system, but the simplest and most direct in terms of agreement with the type of loads that we're working on is to take a sine wave, right? So here's the magnitude of the repeated force, and here's the frequency of the force. So this is the forcing frequency, so that's what the subscript F is going to be. And there's different types of harmonically varying forces that we could apply. Some might be rotating unbalances. So if you, a lot of times we're going to show this pretty soon, but if you have like some type of machine, and let's say that this is the foundation right here, so it's got some kind of a vibrating supports in here, and like something is rotating inside, like that right there, and it's got like a weight over to one side. This is going to cause an up and down motion onto this thing right here, and depending on what the speed of that's going to be, so let's just call that omega F. We could convert it into RPM if that made it any better, and we could see what the response of this is going to be. So in a moment, we will go back and look at this thing and see what the point of our calculations will be. Other things, we could have oscillations due to some fluid flowing by a body. Right here, I'm showing, here's a little graphic picked up off the internet. I think it's actually off of Wikipedia. This is something called vortex shedding. It's related to, in fluid mechanics, you'll learn about the Struhall number. But this has, with a particular diameter and fluid properties, in this case, we have a length. They're calling it a length, but that could also be a diameter, some characteristic length. And it'll have some velocity, speed of velocity. Well, you'll create this omega right there, and that's going to be a frequency. And so the frequency of these oscillations, well, that could coincide with the natural frequency of the body about which it's going in. So that's closely associated with the Tacoma's Narrows Bridge and that disaster. That the air flowing across the bridge or maybe over the cables caused sympathetic resonance and caused the bridge to self-destruct, collapse. Other instances are, and I told stories about being on ships. The ship propeller it only has somewhere about, could be 3, 4 blades. I guess they go up to 5. They might some others, but with every rotation with every blade passing, puts a pressure wave that pushes up against the hull. And for other, mechanisms that you could say that might be being caused by this pressure or the blades moving on, it's a periodic force. And that can excite lots of different things that have the same frequency all over the ship, including like the main hull. Internal combustion engines, right? They have, depending on their speed, they can cause vibration. The same thing with air compressors. There's lots of other pieces of equipment where this could be a concern or maybe even a benefit to some extent, because we have like speakers. You're actually trying to excite the speaker cone by way of the vibrations that are caused by a coil that is moving. All right, so here, those are kind of the ideas that are behind this. So let's take a look at what the main equation is going to look like. So in the first several classes, well, the first class associated with this week, we'll only deal with undamped force vibration, and then we'll put the damping back in there in the next class. So you can see that this, we put this external thing on board it. We should actually call this the FBD, and the IBD is, of course, this guy moving in, I believe, in this direction here. So MX double dot, right? So just to keep them clear as to the way we approach the thing. But you can see that this is a second order, non-homogeneous differential equation. the main things that we're trying to look at is we want to see the forcing frequency versus the natural frequency right here and see how they interact. And instead of solving the problem this way right there, right, where we try to find a solution that gives us a time history, we want to take a look at the relationship between well, I'm trying to find a way to say this. Well, usually we're doing like we're going to go PO over K versus X, right? So this is going to be the input versus the output. You could think of it as being the system response. We put in some kind of disturbance, and I'm trying to make this a deflection, right? So we have force, this magnitude right here, divided by the spring constant right there. We can kind of see, well, what comes out of this? What kind of magnitude of the overfall force? So instead of seeing what it is as a function of time, we actually see what it is as a input versus output, or maybe I should say output versus input. And I should also point out here, when these two correspond to each other, we will predict that we're going to have noise. Well, not just noise, but maybe that's just like one of the small cases of it. We could also have kaboom. So kaboom. I don't know if I spelled that right. Don't spell kaboom a lot. So let's just continue on with this portion of the lecture, because I don't think that many people are going to watch it. So if you watch it, let me know. You say, hey, Dr. Deal, I actually watched that thing. Oh, hey. Oh, cool. So anyway, so here is the undamped version of the thing we just had on the previous page, where we've gotten rid of C. It makes it a little bit easier for us, and we'll be able to manipulate things, and it won't be such a long equation. So if you have this type of non-homogeneous differential equation, what you need to do is solve it in two parts. The first part is the complementary part, and the second part is the particular part. Now, we've already solved the complementary part, right? We already know that we're going to have, as a time function, we're going to have something, let's call it C1 times the sine of the natural frequency times time, plus C2 times the cosine of the natural frequency times time, right? So this, we can consider this the complementary part. But we're also going to have a particular part. And when you have some type of particular part, generally it will look like what the it'll look a lot like the same thing as the input, right? So this is like an input disturbance of our system. So we'd expect the particular part is going to be of the same form. So we're going to go ahead and go xm times the sine of, let's go omega ft. So it's going to have the same frequency, but it's going to have a different type of magnitude. This actually makes a lot more sense in the damped one. We're talking about undamped right now, but in terms of the damped one, we usually think about the damped one as being, diminishing with time. But eventually it'll stop changing because of the initial conditions, and it'll have pretty close to being a steady state output. And that's going to be this particular part. The complementary part in a damped system goes away, and then all you're left with is the particular part. So that's actually a little bit easier to understand. But let's go back to our general procedure. I didn't want to say general because there's general solution. The typical procedure that we do when we have a non-homogeneous differential equation is to take the particular part, right? That's this guy right here, and take the derivative of it. So x dot particular, and you know that's going to be xm times omega f times cosine. Oops, I wrote that wrong. I almost started writing wrong. Sine again. Cosine of omega ft, and then take it again. So we get negative xm omega ft f squared sine of omega ft. All right, so this solution that we're about to do it only really works for the undamped one. So that's one reason why we're doing it. So we're showing the solutions in two separate ways. So if we plug this back into the thing up above, and I don't even really want to do it, but that's okay, I'll do it anyway. So we're going to plug this back up into this equation right here. We'll go negative m times xm omega f squared sine omega f t, and then plus k times xm sine omega f t, and then we'll say it equals po sine omega f t. All right, so just double check that we didn't go too faster here. You can see here is that one. We put him in for this guy up above, and then we took this guy and put him in for here, and then we already had the guy on the left. So we can see that right away that these go away. And what we're left with is an xm is equal to PO over K minus M omega F squared. Now, what did we just say on the previous slide we wanted to do? We want to find this type of thing here. So let's divide through by K. So you divide the top and the bottom. So here's our XM equals PO over K. And then we have K over K minus M over K omega F squared. And you can quickly see that that guy right there is omega n squared, right, upside down, right, because omega n is the square root of k over m. K over m is omega n squared. M over k is 1 over omega n squared. So we can rewrite that out. I think actually what I was supposed to do in the next line was supposed to do that. Yeah, right there. That's what I meant. So 1 minus omega f over omega n squared. Now, look what happens as part of that. This is a really important part. Let's go into highlighter. This guy right here. And I don't write this all the time, so I'm going to try to remember to write it. But we're going to define that. Oops. Get the wrong colors here. We'll go back to pen. And we've been messing around. Let's go with the blue. Let's define a ratio R of omega F to omega N. And when that ratio gets to be 1, we get kaboom, right? That's what's called resonance. And we want to try to avoid it most of the time, unless we're trying to do it on purpose. So what does it mean? R is going to be equal to 1 and kaboom. We have sympathetic resonance. Sympathetic. It is pathetic, I can't spell. Resonance. And so, whereas if you had some other type of spring and mass thing going on right here, and they weren't in the resonance, you could just go boingy, 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 boing. But then if you now correspond the natural frequency, the forcing frequency with the natural frequency, it'll go way crazier than it would otherwise. So some amount of explanation for this, and I'll probably say this at some other class. It's all about the wave speed and wave velocity. If you can picture in a spring, in a long spring here, we have some type of flow. We have a disturbance, right? And that's a wave that's propagating, right? So it doesn't correspond with the coils, but for our purposes, that's fine. And it's traveling. But if it hits a certain spot, it's going to start coming backwards to it right here, right? And when they hit each other, the reflection of this thing, and they coincide, we get all kinds of exaggerated motion. And so as long as we are not in that the speed of this is related to its natural frequency, right? The speed of sound out that's traveling through this, combined with the mass, it will affect how quickly the thing goes and how quickly the bounce back, and when they start bouncing back against each other. And that's why even for multiples of these of the natural frequency will also really respond, right? So there's not just when this number equals one. We'll see in the real world when we get more than 1 degree of freedom that we can have the multiples of the natural frequency can be excited, for with sympathetic resonance by, and we can also prove it mathematically. Um, let's see, is there anything else I want to? Oh yeah, one last thing. So this equation right up here, this guy, we can graph him. In fact, we actually like to put these things over to the side, right? And I think I might have accidentally went a PM. So let me go an O right in here. And then I didn't include what that del M is. And this is nomenclature from another book, so I have to be a little careful with that. But so here is these two things versus each other, right? They are this input, and here's the output. So the ratio of the output to the input versus the ratio of the frequency ratio, and you can see when they equal to 1, we get up and we reach here. So this is often called the magnification factor, right? The magnification factor, which makes sense, right? We're talking about an input versus an output, and whether it's going to be less or more than the input. So the input right here, remember, is PO over K, and the output is XM. So what goes on into here? Here is a graph that shows what takes place. And if they happen to correspond with each other, that omega F and omega N, we go up into infinity because the denominator, as you see, goes to 0. I should have said that earlier. Anyway, but you can also see other places right here, right? So if you have some, we say, hey, we see a response like this, we can come back down and we can see, ooh, it's either that spot or it's that spot in terms of the frequency ratio that caused this output given a given input. So that's what I have for this main part of this lecture, and we'll do some examples next.